I'm going to pick up where I left off yesterday and show you how to balance this equation. So the first thing that we're looking at here is the top of page 3 is what is being oxidized and what is being reduced. So we said yesterday that this manganese went from plus 7, because oxygen's minus 2, so that's minus 8. So from plus 7 to plus 2, that's a change of 5 electrons. Whereas the iron went from 2 to 3, which is a change of 1 electron. On oxidation reduction reactions, the first and really most important thing that you can do is make sure your electrons are balanced. So if the manganese is going from 7 to 2, that means it's gaining 5 electrons. So where did those 5 electrons come from? We can't produce electrons just out of the air, so electrons must come from the other, which is the iron. The iron is being oxidized, but it's only losing 1. So to balance this, if manganese is gaining 5, then I need 5 of these irons. Okay, so that's the first step in balancing redox, is to make sure your electrons are balanced. The last 2 steps are to make sure that your oxygen and hydrogen are balanced, and you won't always need these. But in this reaction, we have 4 oxygens on the right and no oxygens on the left. Well, because these are, I said that backwards. 4 oxygens on the left, none on the right. So because these happen in water, if we need some extra oxygen, we can just get it from water. So on this side, I'm going to add 4 H2O, because that would give me 4 oxygens. Well, then I have too many hydrogens. Okay, so in order to balance the hydrogens, you add H+. So I have 8 hydrogens on this side, so I'm going to do 8 H+ on this side. Okay, so first and most important step is to make sure that your electrons are balanced. So manganese went from 7 to 2, so that was a change of 5 electrons. And iron went from 2 to 3, a change of 1. So I multiply the iron by 5 to balance those electrons. The last step is to add water if you need it to get more oxygen, and then add H+ if you need it to balance your hydrogens. All right, I ask you to read through the rest of those notes on your own, and then we're moving. In this slide, we're talking about how we calculate voltage for these batteries or these cells. So each cell, or metal in most cases, is hooked up to a hydrogen cell, as you see in this top picture. And the hydrogen cell is just assigned a value of 0 volts. So whatever we hook up to it, when we read the voltmeter, that's going to tell us the voltage or assigned voltage for that half cell. So for example, when we hook zinc up to a hydrogen cell, we get a voltage of 0.76. So we say 0.76 is the standard voltage for that zinc half cell. Standard means that we are at 1 atmosphere for our gases, 1 molarity for our concentrations, and 25 degrees Celsius. This is different from standard conditions for like PV equals nRT. We know the standard temperature there would be 0 if we're talking about STP. But in these conditions, when we say standard conditions, we're talking about 25 degrees Celsius or normal temperature. We use the symbol that you see here, this little degree sign, to tell us that it's standard. So if you don't see that, then that could indicate that you're not at standard conditions. So maybe your pressure is higher or lower, or your concentration is higher or lower, or maybe your temperature is higher or lower. But right now we'll focus on standard conditions. This next diagram shows zinc and copper, which is a very popular combination, as we've seen, and it zooms in to show you the electrons leaving the zinc to form zinc plus 2, which goes into the solution. Okay, going in. And then on this side, we have our electrons coming from the zinc into the copper. And as they do, the copper from the solution can then go and form copper solid. So the zinc is being oxidized, that's called the anode, copper being reduced at the cathode. Now here we get a voltage of 1.10. We know from the top here that the voltage for zinc was 0.76, so that must mean the voltage for the copper in this case is our total 1.10 minus 0.76. Notice in these conditions, these are standard. We have 1 molar solutions, and then our temperature is 25 degrees Celsius. There's no gases involved here, so we don't have to worry about the pressure. Okay, I want us to flip forward to page 5, and then we'll go back to page 4 for a second. But on page 5, we have the standard reduction potentials for a lot of different materials. And you'll see that hydrogen is on this list somewhere. Right here, let me highlight it. And it's equal to 0. Okay, so we just say hydrogen is the standard and it's 0, and then we'll hook everything up to hydrogen and see what its voltage is. These are all reduction potentials, so it's all for the element plus some electrons. So you see the electrons are always on the left-hand side. Okay. So in reality, when we hook two things together, though, they can't both be reduced. So one of them is going to be reduced and one of them is going to be oxidized. The one that's oxidized will actually take this reaction and flip it around. So how are we going to be able to tell which one's oxidized, which one's losing the electrons, and which one's reduced? Tables like these are going to help us a lot because the number that we're looking at here, these voltages, these are the likelihood or the potential that these will be reduced. So iron, for example, if we find Fe plus 2 goes to 2 plus Fe, its reduction potential is negative. So that's saying it's not very likely to be reduced. But silver, if we look up here at silver plus 1, there's a silver plus 2 up there, but silver plus 1, it has a reduction potential of 0.8. So it's pretty likely to be reduced. So if we put silver and iron together, silver has a higher reduction potential, a higher potential to be reduced, and iron has a lower value, so iron is probably going to be oxidized instead. So how do we decide? Okay, you're going to decide which metal is oxidized or reduced using the table. The metal, or it could be an element that's not a metal, with the more positive reduction potential is the one that is reduced. And the other metal is going to be oxidized. So we're going to take the other metal's reaction and flip it. So to do this, it says to write both equations as they are with their associated voltages, and then once you decide which one's oxidized, reverse the equation that will be oxidized and change the sign of its voltage. Change the sign of its voltage. Once you change the sign of its voltage, you can then put the two together to find the voltage for the battery that you made, or the cell. So a battery or a cell is made of two metals with different reduction potentials. The one with the lower reduction potential is actually oxidized, so we'll flip it and flip the sign, and then put those numbers together to find our voltage for our entire system. When you put them together, you do have to balance the electrons, just as we did earlier when we saw those two reactions. So to balance them, you're going to multiply so that their electrons cancel. However, do not multiply the voltage values. Okay, do not multiply the voltage values. Once you flip one of them, you can then add them together to find your total voltage. But remember, never multiply your voltages. You can flip them if one's oxidized and then add them together, but never multiply. Just keep that in mind as we move forward. All right, I'm going to keep referring back to that table on the previous page, so you might need to flip, but I won't be flipping like on the actual slideshow. All right, at the top, we want to consider the galvanic cell that's based on the reaction given, which is zinc and copper at the top. Okay, that's the example we've been looking at, but here they give us aluminum and magnesium instead. And they want us to balance it and calculate the standard voltage. Okay, first of all, I want us to think about who's oxidized and who's reduced. So we have aluminum going from +3 to 0. So that's 3 electrons. And were they lost or gained? So they go from +3 to 0. We gained those. So that's being reduced. And then magnesium went from 0 to +2. So that's a loss of 2 electrons, which we would call oxidation. So aluminum lost 3. Gained 3 while magnesium lost 2. So our first step is to balance those electrons. So 3 and 2, how do we balance that? Well, I would multiply the aluminum by 2, that'd be 6, and multiply the magnesiums by 3, that would also be 6. There's no oxygen or hydrogen in there, so now the equation is balanced. I now want to calculate my voltage. So I need to look up the voltage for aluminum +3, and that is -1.66. And then I need to look up the voltage for magnesium, and that is -2.37. Now the magnesium is being oxidized, so I need to flip the sign on this, so that's now +2.37. And then if I put those numbers together, -1.66 from the aluminum and +2.37 from the magnesium, which I flipped, the voltage of this system should be 0.71 volts. Okay, I got these two numbers from that chart on the other page. Okay, and then I flipped one of them, the magnesium, since it was being oxidized, and put those numbers together. Right, in B, we have a galvanic cell based on this reaction, and we want to balance it and calculate the E value. So to balance it, let's look. We have manganese, and this is the same situation we saw earlier. There's going to be a 7 on manganese, and then it goes to a 2. So that's 5 electrons. And then we have ClO3 going to ClO4. ClO3 minus, that would be a +5 for chlorine, and then a +7, so that's 2 electrons. To balance that, we're going to need to multiply the manganese by 2. To balance 5 and 2, we're going to need to go to 10, so 2 times the manganese. And then the ClO3 and ClO4, we're going to have to multiply by 5 to balance those. Okay, now we got to balance the hydrogens and the oxygens. So this could be a little bit of a bear here. So here we have 8 oxygens and then 15 oxygens for a total of 23 on this side. Then over here we have 20 from the ClO4. So that means I need 3 waters to make 23 oxygens, right? 2 times 4, 8. 5 times 3, 15. 8 plus 15, 23. And I only have 20, so 3 more. Right, once I put the 3 there to balance the oxygens, that gives me 6 hydrogens. So I need a 6 here in front of the H+. Okay, so balance your electrons, and then look at the rest of the equation to balance your oxygens and your hydrogens. All right, then they want us to calculate the E cell, but they tell us we're going to need a more complete table, so we'd have to go look up the voltages for these reactions. So we're just going to skip over that part. Okay, we're not going to calculate the voltage here. All right, this is a great question on exercise 2. We need to calculate the cell voltage for a cell utilizing silver metal, so Ag, and iron plus 2 and iron plus 3. So we're going to have Ag and then the iron 2 and iron 3. So I'm going to look back at my chart and find those two things. So for the silver, I find a reduction potential of 0.80, and that's for silver plus 1. And that's the only silver I see other than silver plus 2 to silver plus 1 at the top, but it says that I have silver metal, so I need the solid. Okay, so I'm using the one that's 0.80. Make sure you can find that on the chart. And then they tell me that I want to do iron plus 2 and iron plus 3. So I'm going to find that reaction, iron 2 and iron 3. Let's see, I found the iron 3 to iron solid, iron 2 to iron solid, iron 3 to iron 2. It's on the left-hand side, just below silver actually, at 0.77. Right? So based on this, I would say that silver has the higher reduction potential, so it is going to be the one that is reduced. And then my iron has the lower, so I'm going to flip it and actually oxidize my iron. So I'm going to go iron plus 2 to iron plus 3, so that it's oxidized, okay, instead of going 3 to 2, which would be reduced, because silver has the greater reduction potential, so silver is going to be reduced. If you look at your electrons, silver is gaining 1 and iron is losing 1. So those are perfectly balanced there. If we look at our voltage values, we have a 0.80 for silver and then a 0.77 for iron. But iron is not being reduced, it's being oxidized. So I got to flip the sign. So my voltage here is really low, 0.03 volts. Okay, that'd be a terrible battery to put those two metals together. All right, let's draw a diagram. So let's put a strip of silver right there. And then we'll put some silver ions in the solution. Over here, we'll have our second metal in solution. Now, here we have iron 2 and iron 3, so we don't have any iron solid. So if you remember from the previous video, we should use an inert metal. So let's put some platinum right there, or you can use graphite to be cheap. Okay, either way. Then in the solution, we have iron plus 2 and iron plus 3. Okay, lots of those in the solution. All right, then what else do we need to connect these two? We have our electrons, but we also need a salt bridge. Okay, just kind of a U-shaped tube that has some salt in it. Let's use potassium nitrate as our salt. I don't want to use chloride because silver and chloride make a precipitate, so I'll use nitrate because remember from your solubility rules, nitrates are always soluble. All right, so in our reaction, we have silver going to silver solid, so that means it's being reduced. So that means the electrons have got to be coming to silver. So they must be leaving from this other side. And our voltage, if we had a little voltmeter on there, it would say voltage is 0.03 volts. Okay? Let's label the cathode and the anode. So the silver is being reduced. So this side is the cathode. And then this side is the anode. And remember, the electrons flow from the anode to the cathode. Fat cat. From anode to cathode. This voltage that we're finding each time when we do these, it is related to the free energy of the system. So the equation for that is one that we've seen before, but it's down here at the bottom. Delta G equals negative NFE. If you can see here by the negative sign that E, which is our voltage, and delta G are going to have different signs. So if we have a positive voltage, so if E is positive, delta G is negative, E is positive, delta G is negative, that is going to be a favorable reaction. But if E is positive, if E is negative, delta G is positive, those are not favorable. So how do we use this reaction? we got delta G, we know that that is our Gibbs free energy, equals N. The N here is not just any moles, it is the moles of electrons transferred. So remember from the example above where we had silver +1 going to silver and then 2 to 3 for iron? So each one of those was losing or gaining 1 electron. So our N would be 1. On the example before that where we had like 5 and 2 and we multiplied, the N value would be 10 because we multiplied so that the electrons were balanced and they were balanced at 10. So whatever number of electrons balances the equation, that's your N value. F is 96,485, or we simplified to 96,500, and that value is on your equation sheet. And then E is your voltage. Careful, careful, careful with your units when you do this equation, because as you see, that F value has joules. So when you calculate delta G, it's usually in kilojoules, so you'll have to change one or the other so that your units match. All right, exercise 3, they want us to calculate the delta G value for that reaction using that table of standard reduction potentials. And that table, again, is a few pages back. First off, let's look at this reaction and figure out who was reduced and who was oxidized. So we have copper going from 2 to 0. So that's being reduced by 2 electrons. And then iron going from 0 to 2. So that's being oxidized by 2 electrons. So our N value, we can already see, must be 2 electrons. Those are already balanced. So your N is the number of electrons transferred. Copper gained 2, iron lost 2. The N is 2. For our voltage, our E value, we'll have to look at the chart. So copper plus 2 going to copper solid, that's a 0.34. Okay, if you can find that on the chart. 0.34 volts for copper. And then the iron solid going to iron plus 2, that's an oxidized, so it's going to be flipped from the table. But on the table, it says negative 0.44. Okay, the negative is from the table. But since iron's being oxidized, I'll flip it, so that's positive. So that'd be 0.78 volts for this iron copper cell. That's my E value. Now, that's positive, so that means delta G is going to be negative. But we'll go ahead and calculate it. Delta G equals negative 2 for my electrons, 96,500 for my F value, 0.78 volts for my E value. I'm going to divide by 1,000 to change it to kilojoules. So delta G equals negative 150 kilojoules per mole. All right. Next, exercise 4. Using the table of standard reduction potentials, predict whether 1 mole of nitric acid will dissolve gold metal to form Au plus 3. So let's try to write this reaction. HNO3 plus Au. Can you see this is a single replacement reaction? It says we want to make Au plus 3. So I'm thinking Au NO3 3 plus H2, hydrogen gas. Now the NO3 is a spectator here. Let me see if I can balance this though. So there's 3 NO3s, 2 H2s. So I'm thinking I need a 6 here. That would give me a 2 here, 3 here, 2 here. Now HNO3 is a strong acid, so that's going to dissolve, and then this is soluble. So my nitrate is going to cancel, but I'm going to have 6H plus 6NO3 minus plus 2Au yields 2Au plus 3 plus 6NO3 minus plus 3H2. So get rid of those NO3. So I have 6H plus, 2Au minus, no, that's just 2Au, sorry, no charge, goes to 2Au plus 3 3H2. Alright, so there's the reaction. The reason I wanted to take out NO3 is because it's going to be confusing when you're looking on the reduction potential chart and you're like, I don't see this NO3 on there, or I don't even see HNO3 on there. We need to just look for H plus on our reduction potential chart and look for gold. To tell if this is going to happen or not, we're going to see if it's favorable. So we're going to see if delta G is negative or positive by seeing if E is negative or positive. So first off, I'm going to look at this H plus went to H2. That's plus to 0, so that's being reduced. Then gold, Au to Au plus 3, that's being oxidized. So if I look at the chart, H plus to H2, that's a 0 voltage, because remember that's your standard that everything's measured against. So that has a 0 value. And then the gold going to gold plus 3, let's see, that has a 1.50 value, but it's being oxidized, so I got to flip that. So that's negative 1.50. Put those together and you've got negative 1.50 volts. That means that delta G would be positive if E is negative. So that wouldn't happen. That is not a favorable reaction. So gold metal dissolving in acid is not favorable. This is good news. This means that your gold ring, if you drop it in some acid, it will not suddenly dissolve. So what's the point of putting a gold ring in acid if it doesn't dissolve? Well, the acid will clean off everything else and leave you with your gold metal because the gold will not dissolve in the acid. So that's great. But that is not favorable.